Alright, so here's where I'm at right now. Okay. Exponentiation. They both start at 1. Exponentiation of x to the n on u for all integer n and all real x and u. I don't like either of these categories because they are based in philosophical bullshit, but because nobody understands how anything works, we have to start from where the stupid people think. Okay, so first off, the magnitude. Starting at 1, we multiply that by x, n on u times. And I've shown before that that works in all cases. The unit, this is the part that was missing previously from my account, and is apparently missing from fucking everyone else's account too. So, yeah. Starting at 1, k is equally you get k equally distributed solutions on the complex unit circle. There you go. And that actually explains everything. And this could be simplified even more because starting at 1 happens on both of them. So that doesn't need to be part of either of them. Which is really nice because you can raise bare units to exponents. So, yeah, okay. Anyway, so everything below this point is being said exclusively to clear up dumb shit that's widely believed at this point, as far as what I can tell. If irrational, the fraction n on u should never be written with the irrational as a numerator and an artificially introduced integer denominator. Okay, this should be how fractions are always done, because that doesn't make any fucking sense. An irrational is a valid unit type, but not a number. Denominator is, it denotes your unit. The numerator denotes your fucking number. So, we're like, oh, I don't like square root of 2 on the bottom, so if square root of 2 on 2, that's better than 1 on square root of 2. Fucking Christ. Note that after a full orbit of the full unit circle, we return to positive 1, not 1. The need for this distinction appears to be what has people spooked about ambiguity in dealing with Euler's formula. 2 to the 0 is 1. This is the dimensionless multiplicative identity, not positive 1, because the exponent is 0 on u, which means the result is not imbued with a unit. Right? This comes from this part. Right? So even when we're dealing with bare magnitudes, the unit component is actually relevant. 2 to the third is 1 times 2 times 2 times 2. Multiplication occurs 3 times. We live in a world where we say that there is an operation after exponentiation called tetration, and the way we get there is we build up from addition, which is our first operation. We iterate that to get multiplication, that's our second operation. We iterate that to get exponentiation, that's our third operation, and then we iterate exponentiation to get tetration. But when we actually explain to children, and to students, how to do exponentiation, we do not show them iterated multiplication. We showed them, we cut off this part, and actually we're just completely unaware that that should be there in the first place, which leads me to wonder, how in the name of fuck did you perceive that this is iterated multiplication when you don't do it as iterated multiplication? Anyway, 2 to the negative 3, 1 iteratively divided by 2, because the negative of multiplication is division. 2 to the 1/2 gives us 1 times n, where 1 times n is 2 to the first. So these two n's here is the 2 in the denominator of that fraction. Right? So over here I show it a little bit better. But note, n has 2 unit definitions. It can be positive and negative. And 2 to the 7/6, where 1 times is 1 times n, where, oh wait, I did that wrong. There we go. Now it's right. I have it down here too. Plus 2. There we go. Where 1 times n 6 times yields 2. N has 6 unit definitions, including positive. Always including the positive. If this is non-zero. Two to the 1 on pi yields 1 times n, with n having every possible complex unit. This is important. I'm pretty sure this is completely missing from everyone's account up to this point, but it's true. There's an infinite number of solutions here. The magnitude you can find with a calculator, but all of the possible solutions you cannot. Note that for integer exponents, the only way for the result to have a unit is if the base has an explicit unit in the first place. This is the true source of the quote-unquote ambiguity that has people spooked. So, e to the 0 I pi, that one value, is indeed distinct from e to the 2i pi, and e to the 4i pi, and e to the 6i pi. Okay? That 0 I pi value is distinct because that is the dimensionless multiplicative identity 1. And the others are positive 1. But all of the others are exactly the same positive 1. They're not distinct from each other. Once it leaves, once you apply any torque off of the number line, you get vectors instantly. And from then on, the unit component cannot be separated off. It is part of it now. And so whenever you come back to 1, you're coming back to positive 1, right? It's a completely different beast from the number 1 that you started with. That is where the ambiguity is. And I think what happened is, because it happens right away, people got the impression, oh, it happens everywhere. No, it actually just happens right there. And every positive 1 after that is the same fucking thing. So here, go through the same thing, but with the positives, so you can see it, and really the wording isn't different. So 1 to the n on u involves absolutely no ambiguity at all. That positive 1 is not a specific imaginary power of e. It is e to the I n times 2 pi for all non-zero integer n, simultaneously. Believing that you should somehow magically be capable of discerning which one it is just absurdly arrogant, especially when coming from a framework that can't even distinguish 1 from positive 1, despite actually having the ability to write those differently. So, this is not my final form because I'm pretty sure I can pull out this starting at 1. Starting at 1, multiply by x, n on u times, and you will get k equally distributed solutions for the unit, equally distributed on the complex unit circle for the unit. There you go.